Hey folks, in this video we're going to be talking about light maths, or mathematics related to the electromagnetic spectrum. Figuring out how juicy them photons are. This is a photon, apparently. Anyway, our objectives are, I would like you to be able to calculate the frequency of a photon using the speed of light and wavelength, or calculate the wavelength of a photon using the speed of light and frequency. And I'd also like you to be able to calculate the energy of a photon using frequency and Planck's constant. What is Planck's constant? We'll find out. New vocab would include hertz, which is a unit, and dimensional analysis, which we've actually done before. I don't know why that's in there. And joules, another fun unit, and we're going to use Planck's constant, represented by a lowercase h. I guess it's backwards, so there we go, lowercase h. Let's get going. So we have two main equations that we're going to talk about or utilize when we're doing mathematics for photons or electromagnetic radiation. And this is our first equation. It relates the speed of light to the wavelength and frequency of a photon. C is our constant for the speed of light, and we know that lambda, this upside down Y looking dude, is frequency, and V or nu is our I said that wrong. Lambda is our wavelength and nu is our frequency. And so we can rearrange this equation if we wanted to solve for wavelength or frequency. Speed of light C is a constant, will not change. So we can rearrange this so that V is equal to speed of light, or nu is equal to speed of light divided by lambda. And we could also rearrange this so that lambda is equal to the speed of light divided by nu. Whenever we're using these equations, though, all these equations, we need to make sure that our units are correct when we're plugging them in, because the units for these things have to match up real nice. So speed of light, we're always going to be measuring in meters per second. Wavelength, whenever we're doing math with the speed of light, we're going to measure in meters. You may not always be given a wavelength in meters, but if you're going to do math, it's important to convert your wavelength into units of meters. So yeah, you might see it come up in nanometers or micrometers or even kilometers. Many units are given for wavelength, but we can always convert them back to meters when we need to do math. Frequency generally is going to be given in units of 1/seconds, inverse seconds, which we also call hertz, which is symbolized, I don't know why I have it here, but a capital H with a Z next to it. And so, as I said, these equations can be rearranged. Here's the primary equation we use, but here are those two rearrangements that we're going to use most often because we're going to solve, those are the best ways to rearrange it. These are the only two ways to rearrange this equation, actually, or two alternatives. Anywho, let's do some examples with that. So we've got a photon, and its wavelength is 5 meters. What is the frequency of this photon? Well, the first thing we're going to want to do is rearrange our primary equation if necessary. Pick which way we're going to use this. And so we want to solve for frequency, so we should rearrange it so frequency is all by itself on one side. We need to make sure that our units for wavelength and frequency are correct. They need to be in meters and 1/inverse seconds, or 1/hertz. So we can look at this and say, oh, 5 meters, that's pretty chill. So this might require unit conversion. Not in this case, though. And so once we've got our units correct and our equation rearranged, we're just going to plug in and solve for that unknown. So let's do it here. I've got my equation rearranged so that frequency is all by itself. I want to solve for frequency, so we should get it all by itself. My units are already in meters, great, and speed of light is always in meters per second. So all I need to do now is plug in. So I will divide the speed of light, C, by my frequency. And that will give me my answer of where are my words at? Frequency. Now, one thing that you're going to find a lot in these light maths is that our answers are very, very often expressed in scientific notation. So if you aren't feeling really awesome sauce about your scientific notation skills, you should probably check out my other video on scientific notation. All right, well, let's keep moving with another example. And why don't you pause the video and try this one out meow. You know what? Actually, you might find it a little difficult. Let's advance this a few more slides. We'll go through the wavelength, but here we do not have units in meters. We have units in nanometers. So we're going to need to do a unit conversion. And so here's the conversion factor you might want to use. You're definitely going to want to use that. Why don't you pause the video and see if you can tackle this problem now? Sick. You pause that video. Well, first thing we're going to need to do is some dimensional analysis. We're going to need to convert our 510 nanometers into meters. So we will multiply that by this conversion factor, putting our old units in the bottom so that they're going to get canceled out. And then we will just multiply through. So we'll do 510 times blah, blah, blah meters. And so this is going to give us 510 times 10 to the minus 9th. And we're just going to change this to be correct, because whenever we use scientific notation, we want to have one number in the single place, one digit in the singles place, and then decimals after that. So I will advance my decimal place 1, 2. And when I move my decimal place forward, I'm going to increase my my exponent. Pardon me. I'm going to increase my exponent by 2 because I moved my decimal point 1, 2 spaces forward. Okay, cool. So I've converted my units into meters, and now I'm going to just plug in. So I will divide my speed of light in scientific notation by my wavelength. I'm sorry, my frequency. No, my wavelength in meters. Scientific notation also, and I get a super cool answer in inverse seconds or hertz for my frequency. Sick. Cool, let's keep going. Oh my god, look at this cat. Look at the cats and the rabbits. My mouth is having trouble today. But this cat is clearly afeared of these rabbits, and these rabbits are just like, yo, what's up? I just love this. Anyway, let's talk about the other equation that we're going to use for light math. This is energy is equal to Planck's constant times frequency equals hv. Planck's constant, well, it's constant, yes, and it's got some pretty wild units, and it's also a pretty absurdly small number. Look at that, 6.626 times 10 to the minus 34th. That is a super small number that I would never like to write out in non-scientific notation. And so energy, the units we're mainly going to use for energy are joules. There's many ways that you can measure energy, but we're going to use joules for the most part, which is pronounced like joules, but they are different, although they're both precious. And so we might see units of kilojoules or megajoules, other prefixes applied to joules. That's pretty common, particularly if we're talking about like large-scale energy production. Yeah, so we might see those fun friends. And so we can rearrange this equation if we want to. If we want to solve for frequency instead of energy, we can rearrange it so that frequency is equal to energy divided by Planck's constant. And there is another cool way that we can rearrange this through substitution. So if we take this equation from our rearrangement of our first equation, we can take V and substitute C divided by lambda into this main bad boy. Let's look at that. So it would look like this. And now we can use this equation, which has energy, 2 constants, and wavelength in it, if we want to directly convert between wavelength and energy. We'll see an example of that later, but it's pretty fancy stuff. I feel fancy anytime I use that. So let's do some practice problems with that E equals hv equation. We know a photon has frequency of 5.00. Well, you can read it. What is the energy of this photon? Why don't you pause the video and try this out? We're going to follow the same procedure as the other stuff. Basically, substitute, make sure your units are good, and plug and chug. Okay, cool. So you paused it and checked it out. Well, we're going to use this equation because we have energy isolated, and we want to solve for energy. We always want to have our unknown isolated. Our units are good to go here. We're supposed to have units of 1/seconds for frequency, and that's awesome. So we can just plug right on into this sucker. So energy is equal to Planck's constant times our frequency. The only difficult part might be plugging in your scientific notation if you have a weird calculator. Anywho, we can solve this, and bam, easy peasy, done. Super easy peasy. Let's look at another problem that's a little bit spicier. Why don't you pause the video and try this one out now? Cool. So for this one, what we're going to need to do is rearrange a little bit because we want to get frequency. So we'll have to rearrange our equation to that E divided by H equals V, or frequency. But our units are in joules, so that's super cool. So we can just go ahead and plug right in. We'll do our energy divided by Planck's constant to get our frequency. And if we wanted to identify what kind of electromagnetic radiation this is, well, if you weren't able to figure it out, why don't you pause the video and try it out now? Cool, you thought about it for a second. So if we want to figure out what kind of electromagnetic radiation this is, I'm going to look at my frequency. All right, I've got frequency up here. This is approximately 1 times 10 to the 10th. So that would be right in this microwave region. So this would be a microwave photon. Cool stuff. Let's look at another example. Here we've got a photon with a wavelength that's given to us, and we want to go directly to the frequency. So we're going to use our super cool rearranged equation. You know what? I shouldn't have told you that. Why don't you pause the video and see if you can do the rest of this sucker? Cool. Well, our units are already in meters, so that's great. We don't need to do any conversions. We can just plug right into the equation. So we'll do Planck's constant times the speed of light divided by our wavelength, and that should give us our energy. Super sweet stuff. Cool. Let's look at another problem. Oh, I guess that's the end. Well, I hope you understand how to do mathematics with light, or math for those photons in calculating their wavelengths, their frequencies, and also their energy. Ta-ta. I hope you have a great rest of your life.